Hello, what's up, ladies and gentlemen? This is Papa Bale, and welcome to the channel. We're here building a new pulse motor generator. And since, we 3D printed a rotor, 14 inches in diameter, with 12 neodymium magnets they're sticking out 10. They're in the recessed 10. So they're 20 millimeter magnets, and these 40 millimeter diameter.
So you're able to CAD the design to have the magnets fit with glue.
Yeah, basically I didn't really have to hollow them out any. Basically I could hammer them in. So they were really nice and tight. 3D printer made it basically seamless. So it was really tight, fit, and the glue, just, they can still pop out. I'm not saying they can't pop out. But right now it's pretty solid. Alright, so we got this toroid magnet here and this one on the table. They're set to repel each other. I knew something was around with that. Okay. You gotta get bearings. You gotta make a hole in the center when you're printing it. The bearings gotta fit in the hole, and then the center or inner diameter of the bearing has to fit around the shaft.
And the shaft is fixed in there. Let me show you. With screws. All right.
And then you there it is. Yeah, this is not easy. Alright, ladies and gentlemen, we'll be right back while I get this on. Thank you. Alright, we got it. And then since it's a pulse motor, and we're going to pulse it with permanent magnets. Permanent magnets will provide our pulse. And every time a permanent magnet passes past either this coil or this coil, it'll turn the power on. It'll complete the circuit in the transistor, and it'll turn the power on.
All right, so now explain the coils.
These coils are 32 gauge. This one is 8,888 turns. And when the magnet passes, it'll generate above 0.5 electricity, 0.5 volts, turning the transistor on. And this has got about 6,000 turns in it. It's 32 gauge. It does the same thing. But if you look straight down at it right now, these two are on set. The magnets are right there, and these two are offset right now. You see what I'm saying?
Yes.
Awesome. And so, and like, it's always on. Even though it's a 12 magnet motor, it's always on. You just can't line it up at 180 degrees because there's magnets at 180 degrees. Okay. Those base, I'm gonna say they're base coils because they just turn the base on in the transistor. But they are powered by what I'm trying to say is the collector on a transistor that provides the input voltage is run by our drive coils, and these are 26 gauge wire, 4 strands with 215 turns wound in parallel, hooked up parallel. So there's 4 transistors for this coil. And then this coil right here, same deal. Same deal. 26 gauge, 4 strands, 215 turns, 4 transistors. And then the toroid magnets, of course, are repelling. Look, I just tap it a little bit and it'll go, basically. Not very fast, of course, but it's moving. Alright, so we discussed the drive, we discussed the pulsing mechanism, we discussed the rotor. Should we turn it on?
Nope. What are these cords? How do you get these fixed? How strong is the table?
How strong is the table, dude?
It's strong, but
I'd say
it does
is pretty
shake.
strong. I mean, like, I built the table. I went down to Home Depot or Lowe's or something to get some wood, and like everything they had was warped. You gotta buy it online basically not to get warped wood. It's crazy. So I got what I could, straight as I could, in back, put it together. What I wanted to do was I wanted it to rest, and then I wanted to have everything be elevated off the ground, the shaft. Didn't want the shaft on the ground, so, and I originally had bolts all around the whole thing. And I wanted to connect everything together through the pulse motor in this like electrical fence of bolts and copper.
Yeah, I remember that.
But you know, that idea fell through. I mean, everybody kept on saying you can't use bolts. I'm like, dude. You can't use when you really shouldn't use bolts. You should use something else like iron spikes or something. But I used the bolts. I just never got the copper up on them. But it was supposed to be able to link, like say this part of the board to this part of the board without you ever seeing that link, except for connecting to the terminal, which would be the bolt sticking out of the top. All this would be going on underneath the table. So, and that can still happen. I can still do something crazy like that.
Because when these things start spinning fast, the shaft
starts shaking because on the one before we had 2 stacked up,
right.
2 pegboards, and the other one's over there on the wall. I decided to use 1 because I had all that extra support in the center, but it doesn't go all the way up. So
Okay.
there's still like a dip there, a bow. So I would say it's strong up to about 1,200 RPMs.
Okay. And then, so each one of these coils has copper strand coming out of it with enamel on it, and then you have these clips. Now, what are these clips for?
They're to connect basically to make all the connections you would with a breadboard. I've made with clips. For one, these transistors, their pegs, their legs are fatter. thicker than the ones that fit into a breadboard.
Right.
So I just decided to do everything outside the breadboard until you run out of negative connections to your power distribution, and then you gotta connect power distribution to a breadboard, and then you gotta infinite more connections that way.
Right. Nice. And then I guess the last piece is this piece.
This is a 25 volt, 20 amp power supply, and this is a 60 volt, 8 amp power supply. And I got this to work last night using this coil right here.
Yeah, that was fun. Yeah.
So, yeah, I think that if I can get that to work using this coil, this thing can run itself at least for a little bit.
And then, turning it on is
the next step. Huh?
The next step.
All right, so we're going to do 1 volt. Sound like a plan?
Yeah. So that is power on, coming from the plug. So now, in summary, what have you now created?
I've created a low energy pulse motor. We've just built a new low energy pulse motor that at less than a volt. Bear with me while I hook this up. We're going to put this meter in right here. I want these to be untangled. I don't know how I got so bad. This, I've never got the reading on the 12 magnet rotor, so we're all about to see what's going on here. Okay. $32. That's nice.
32 AC volts.
Yep. Now let's see about wow.
50 milliamps.
So that's about the same as the 9 magnet one.
And then what is this?
This is a multimeter oscilloscope, and we're currently looking at the current or the amperage of this coil right here. We got hooked up to this bad boy right here, and we're generating 109 milliamps.
And this is up to 1.21 and 0.1.
It'll go back down. And this one's going up too, by quite a bit. That's interesting how the momentum of this has now exceeded the power input.
Right.
So that's what's going on over there.
All right, so in conclusion, to build a new pulse electric motor, what are the main things that you need?
I would say you need a rotor at least an inch and a half in diameter, if not 2 inches. 2 inches would be good for me. That's almost too small. There's no real defined biggest you can do. This is 14 inches. It should be round as possible. You should try to recess the magnets all the way if possible. Shouldn't have any sticking out. You should have like an aerodynamic spin. That's just the rotor, and then you should either do 2, 3, 6, 8, 9, or 12. You can do whatever you want, but I mean, is the more symmetrical or it is, the more it'll make sense.
12 what?
Magnets. I'm sorry, I was thinking that. I just never said it. For your rotor. So 2, you'll be going max RPMs, I would assume. 4, you'll maybe go faster with 4. Not exactly sure, but I think you get more output per magnet with more magnets.
And then you just have to use, what do you have to use? You just have to know degrees and where to place the magnets.
Well, you can use a protractor, full 360 degree protractor.
If you don't have a 3D printer and CAD design software, yeah.
I'm just talking like if you're going to draw a picture on the rotor with a pencil, you need one of those. They're really neat. They're really neat. They're circle.
I like them.
Yeah.
So make sure, that you're dealing with the circle. Okay, and then the coils.
Yeah, the coils are really small, as you can see, and they respond with very little input.
So the coils are the way that the electricity from the wall interacts with the rotor with the magnets.
Sorry? What do you mean by that?
So tell me why the coils are important. Tell me why they're needed.
Oh, electromagnetism. That's how it operates. That's why we need to pulse it. So a pulse will push it along, and at the same time it'll bring forth the next magnet, and it'll push it along. That's why I have these ones extending out 10 millimeters, so you get the other side's effects better.
Very nice.
But yeah, when you put the electricity through it and you pulse it, it imitates, it causes the motion. I'm not scientific about it. What I'm saying is it causes the electromagnetic force causes the force of the permanent magnet to repel.
Got it.
And at the same time, the next magnet is being attracted.
Got it.
At least with a 12 magnet motor, you could do it that way. But when it gets to this point, it switches. You know, the coil. This coil will pulse it, and it'll switch again, and then it'll repel and draw and repel, draw and repel.
Yep, from very low input, and then I think just making sure you know about connections and transistors.
Yeah, let me think here.
For circuits. Yeah.
Let's take a look at the wave.
And then testing. Yep.
So we're at 21 hertz. All right. $2.5.
And as more power is put into the system, the waves become
Get more
tighter.
voltage.
And then the numbers on the bottom there change.
Frequency increases and the voltage goes up.
Yeah. So hertz on the right, volts on the left.
What are the hertz now, bro?
35,
Nice.
36. And you can see it, you can hear it just increasing. And that's reflected in the data. So
3.2.
nice. You can hear it.
You can see it shaking.
Yeah. So rotor, magnets, bearing, shaft, coils.
Might I
Connection
make a
clips.
suggestion for a rotor?
Yeah.
Yeah. To have a rotor manufactured for you instead of trying to do it yourself. This is key. And everything's starting to shake because it's that much off balance.
Yeah.
That much, man. It's just that much. That's all it takes.
But it is a beautiful, complete piece. And then it's customizable, 100%, because the coils, we make the coils right here. And then each one has a different way of affecting the entire system.
72 different individual lines here. That's how I make my maglev coils, or my maglev permanent magnet things. All right. Thank you very much. Peace out. Thanks for coming in and being enlightened and enlightening me. Thank you so much. Bye now.